Hello, everyone. My name is Jonathan Alvindo Fernandi, and I am here to present our research on identification of biomarkers for brain cancer, integrating bioinformatics and deep learning. This work was done in collaboration with my colleagues, Vinson Luckianto, Ms. Gina Zainabila, and Mrs. Judika Vimoniaga. Let me start by giving an overview of the presentation. I will first introduce the motivation behind our research, followed by a discussion of related works. Then, I will describe our methodology in detail. After that, my colleague Vinson will present the data analysis and results and conclude with the key takeaways and future directions. Brain cancer is a significant global health burden. In 2020 alone, over 300,000 people were diagnosed with brain tumors, and more than 250,000 died from brain and CNS cancers. Early and accurate diagnosis is critical for effective treatment planning and improving patient outcomes. MRI plays a crucial role in brain tumor diagnosis, but manual analysis is time consuming and prone to variability between radiologists. This motivates the need for automated AI models to identify and classify brain tumors from MRI scans. To put the impact of brain cancer into perspective, a person's lifetime chance of developing a brain tumor is less than 1%, but it is still the 10th leading cause of death for both men and women. This data underscores the importance of our research in developing better diagnostic tools for brain cancer. In conducting this research, we asked key questions like what specific problem are we trying to address? Where can supporting research be found? Why is this topic important? When did research on this begin? Who will benefit from this work? And how will the methodology be implemented? Answering this guided our approach. The dataset we used consists of 7,023 brain MRI scans obtained from Kaggle. It includes scans of glioma, meningioma, pituitary tumors, and non-tumor cases. Several recent works have made significant advances in applying deep learning to brain tumor analysis. For example, Pei et al. Developed Kenet, a unified framework for tumor segmentation, classification, and survival prediction using methods of CNN. Kureshi et al. Created a radiogenomic model that fuses MRI and genomic data to predict a key biomarker with high accuracy using CNN. Tabassum et al. Reviewed the importance of integrating radiomics with multiomics data to identify novel biomarkers using methods such as CNN. These works demonstrate the potential of combining bioinformatics and deep learning of CNN for brain cancer diagnosis and prognosis. Now, let's dive into our methodology. We first pre-processed the dataset by splitting it into training, validation, and test sets using stratified sampling. We used data augmentation techniques like rescaling and brightness adjustment on the training and validation sets. For the model, we used a pre-trained exception CNN, removed the top layers, and added custom layers, including flatten, dropout, and dense layers with RealU and softmax activations. The model was compiled with AdaMax optimizer, categorical cross entropy loss, and metrics like accuracy, precision, and recall.
Thank you, Jonathan. Now, I, Vinson Luckianto, would like to present the data analysis and results in detail. The model was trained for 10 epochs using the training and validation generators. We visualized the training metrics to identify the best epochs for each metric. For evaluation, we calculated the loss and metrics on the train, validation, and test sets. We generated the conversion metrics and classification report to analyze per class performance. The train model was safe for easy deployment. We created a predict function to load an MRI image, generate predictions and provide a detailed descriptions of the predicted tumor type. Here are some key results. Our model achieved an impressive accuracy of 97.89% on the test set, with high precision and recall scores across all tumor types. It showed exceptional performance in detecting absence of tumors and classifying pituitary tumors. The confusion matrix and classification report provide a detailed breakdown of the model's performance. Here we see an example of the model's predictions and detailed tumor descriptions it generates. The prediction function loads an MRI image, displays the probability distribution, and provides an overview, symptoms, treatments, and relevant specialists for the predicted tumor type. In conclusion, we propose an exception CNN model that can accurately identify and classify brain tumors from MRI scans. It demonstrates the potential for non-invasive brain tumor diagnosis using deep learning. By combining bioinformatics and deep learning, our approach can contribute to improved treatment planning and personalized medicine in neuro-oncology. For future work, we plan to integrate additional imaging modalities and multi-omics data to enhance performance and gain biological insights. We will validate the model on diverse datasets to ensure generalized stability. We also aim to develop a unified framework modeling the interplay between segmentation, classification, grading text, and optimize the model for real-time use in clinical settings. That concludes our presentation. Thank you for your attention. My colleagues and I will be happy to answer any questions you may have.